So what we're going to do now, there's actually two labs that we're doing. One is the heart sounds lab, one is the EKG lab. It might be more fun to just start with the heart sounds ones because that's something I'm not talking at you. So let me, so. So unfortunately, we are not going to be able to do actual, like, take a stethoscope and put it on your partner, which is actually really cool. And you can actually hear the boop, 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 boop. Some of you have probably done it before. I'm sure you all will get an experience to do it. But what we're going to have instead, at least so there is something to do. Well, I do want you to at least, if you haven't heard it, to hear it and think about what the sounds mean. So there is a little video that's just somebody explaining it and kind of showing what's going on. And I made a little quiz just to like double check a few things on that. And then the other part, which you can kind of do together on your own, is the thing about feeling pulses. So the pulse pressure, we talked about the pulse pressure. Does anybody remember what the definition of pulse pressure was? We talked about that when we did the blood pressure lab.
It's systolic pressure minus diastolic pressure.
Uh-huh. So when you are feeling your, let me stop sharing. You know, if you've got your hand, on your radial artery here, you're basically feeling the pressure is increasing up to systolic and down to diastolic, up to systolic, down to diastolic. Pressure is just force per area. So what you're feeling is that blood pressure force pushing against you, expanding the diameter of that artery, and you can feel it kind of moving under there. This is used clinically, obviously just to take somebody's pulse rate, but it's also used to detect if you have adequate blood flow to different parts of your body. People will feel the pulse at the extremities and we'll see if it seems like there's an adequate pulse or if it seems really weak, maybe there's some problem with blood flow to that region. So part of our lab, it's part 2 of the heart sounds, it's in your lab notebook or lab manual, is trying to feel the pulse at different parts of your body. Maybe I can actually share this part. Let me share screen. This is in your lab. You have this thing where it says, check the temporal artery, check the facial artery, check the common carotid. Some of these, you have done in the past, so you don't have to probably do much. Let me get like the, for the temporal artery, you're going to feel up near your temple. That's usually pretty easy to find. The radial artery, that's the one you're all super used to. It's near your thumb. The radial artery is on the thumb side of your hand. You just feel it, you can feel it thumping. Carotid artery, the one supplying your head and your brain, you can feel on the side of your neck. That one's pretty easy. We did that in the blood pressure lab. Some of the other ones get trickier and trickier. Facial artery, you can feel it. It's kind of like near the angle of your jaw here. but it takes a little more work to find. Brachial artery, hopefully you have felt, because that's what you needed to find for your sphygmomanometer lab. These other ones, so these are useful, again, both in terms of taking pulse, in terms of seeing, like, you know, you'll feel the dorsal pedis artery to see is there adequate blood flow coming all the way down to the extremity. You also can use these as pressure points to stop the blood flow. We're going to see that in our lab today. Just watching how the blood flow to the hand gets changed by just compressing like the brachial artery. So if somebody has some accident and you're trying to stop the blood flow, you can know where these are and push on them. So what I'm going to have you do, I kept a list of who's in which breakout rooms. So I'm going to put you all into breakout rooms. And what we're going to do is have you in your breakout rooms. Obviously, you're not going to be feeling them on each other. You're going to have to just feel them on yourself. But I want you to kind of share what your experience is, you know, and write down what your experience of these different pulses are. Are they strong? Are they weak? What do you notice? There's like a little 3-part quiz that you can all do together. It's in the module for heart sounds. If you kind of look here, it's, you know, basically this little quiz saying, you know, about, you know, things about the heartbeat. So you're gonna, actually, I want you to go to the module. Let me find the module. So doing the lab, heart sounds. Basically, there's a little like YouTube that you can watch that describes the heart sounds. And then there's this little quiz that you can take. In fact, you can't take, that I would like you to take, that you can all work on together, where you can just, you know, agree on what your answers are and submit that. It'll also, again, include your descriptions of like where you felt you had more stronger or weaker pulses. And then after we do that, we'll all kind of regroup and come back and do the EKG stuff. But I figure, again, I still want part of the lab to feel like I'm not just talking at you, and like that you get to talk with each other. So are there any questions about this? I'm about to push you into the breakout rooms again, and what I'd like you again to do, look at the video of the heart sounds. It's just 4 minutes, but kind of think about, you know, it's going to go into details about murmurs. Don't worry. You should know what murmurs are. You are not going to be responsible at all for the different kinds of murmurs or anything. So don't worry about that at all, please. But you should think about what is causing the LUP and the DUP and things like that. And then after you've done that, do the part 2 of the lab where you're feeling your different pulses, you know, and share, you know, do it along with each other. So you can all feel and you can all discuss. Yeah, I can feel it. I can't find it. Oh, maybe, oh, did you look here? So see if you can help each other find some of the trickier ones. And also know you might not find some of them all. So that's an okay thing as well. And after you're done, you'll do this little quiz, which again is 3 questions, but including an essay question about the pulse. And then maybe regroup and like, that's not going to take that long. Let's say in a half hour from now at 10:40, we'll kind of come back and then start the actual EKG part of the lab. So are there any questions about that? All right, so I am going to create the breakout rooms now. And screen here. Where did people experience the strongest pulses?
Common carotid.
Carotid's a really strong one. That's again why we were taking the pulse. Where's another really strong one?
Radial.
Radial. The other ones, how about, did anybody find all of them?
I didn't find the femoral, the tibial, or the pedis arterial, or the
Or
dorsal.
dorsus pedis?
Yeah.
The femoral in general, you just have to kind of go, it's coming down kind of right in your, in front of your thigh, a little inside towards the groin there. You can usually feel that one. I mean, this is one, even if we weren't like sheltering in place, that is one of the ones you would feel on yourself and not feel on somebody else anyway. But
Does it feel it? I can't feel it still.
did anybody feel their femoral artery?
Yes.
Yeah.
Mm-hmm.
If you kind of just like search around, you'll probably find it.
Is it supposed to be strong?
That one's pretty strong. The other ones, like facial artery, you can feel, but it's very subtle. Dorsal pedis, like the popliteal, I can say depends on the person. On some people, I feel for it and I can feel it. And some people, I really can't find it. So sometimes it depends on the person as well. But yes, I think it's kind of fun. And the idea of a pulse is not just the rate, and it's not even just the amplitude. People also try to feel like how impulsive it is. Is it kind of like boom, boom, or is it more kind of soft, like ooh, ooh, right? You could be strong, but kind of having this kind of soft ooh, or strong and boof, boof. So there's a lot of different qualities beyond just the amplitude and just the pulse rate that you can detect. In some, like in traditional Chinese medicine, they do whole pulse diagnoses. They can tell all sorts of stuff just from the quality of what the pulse feels like. And even in Western medicine, they spend a lot of time looking at pulse beyond just the basic, things that you're thinking about. So just kind of putting that out there, that your pulse is more than just like, what's your heart rate? So let's do the next part, the EKG. Again, typically you would put electrodes on your skin, and the voltages generated by the depolarization of your cardiac muscle shows up on your skin in an easy to measure way. And there are lots of different like subtleties to EKG. There's different leads. In the lab book, I put like lead 1, lead 2. And then you can actually, by looking at the differences in what the EKG looks like, measuring across the arms or the arm and the leg or this arm and that leg, you can actually get a sense for the axis of the heart. And again, if you're doing a more elaborate EKG, there's like these 12 little leads and these little suctions that they put on there. But again, for our lab, it's just kind of first approximation. Let's at least see the P, the QRS, and the T waves. Getting a good signal is really about getting a good connection to the body. So you'll see in this video, Tina is going to use, we have kind of like little ghetto skin exfoliators. They're basically little cut up Scotch-Brite pads, but kind of trying to get the kind of dead skin off and cleaning the skin and putting the electrodes on. So I'll just do it. We have in this module, which I'm going to bring up for you all now, share screen module. Basically, we went in and this first part is just observing and recording the EKG. So this is like in the old days when I used to do EKGs, you would, maybe I should let me stop sharing just for a moment and mention one more thing. Like old school, it was a roll of paper on this little, it's called a strip chart recorder, and the paper would keep rolling and pulling along. There would be a little stylus with an ink, and it would just all be analog. The voltage on from your EKG drove the movement of this little stylus up and down, and the paper kept rolling along underneath it. And it would draw the EKG, and the paper had graph on it, and it went at a speed where you knew like every little box on the graph paper was like a tenth, what is it? Like a tenth of I think, or 2/10 of a second or something. Modern stuff is all using a computer to digitally sample your EKG and then put it on the screen. But it looks just like it would if it was recording it on the old school. But it makes it easier to measure times. It makes it, you'll see, we're going to show you can like make it look bigger, make it look smaller, spread out the time scale, contract the time scale, because it's all just data now in the computer, and how you display it is easy to change with a little click of a mouse. So this is going to be taking the EKG in the modern world of analog to digital conversion. And yeah, we'll just watch this. This just lasts a few minutes. And I was messing around with some cool 3D font stuff. All right, so we're gonna start connecting things.
So maybe the screen.
All right, so we have the software that actually is going to be running the little analog to digital converter. All right, so then we've got the lab chart running. And now let's see how we hook people up.
Picture of the hookup and the box. All right, removing jewelry, watch, plug in the bioamp cable into the bioamp socket.
I'm going to show how that actually goes.
Connects the 3 leads to earth, ground.
Those little things with the snaps, those are the electrodes.
Pulse transducer, actually can pick that up. So this will be for later, not for the EKG. This is for looking at pulses.
Yeah.
All right, let's
so we
wire up our subject.
Attaching. Yeah, so that.
I should just mention, so this system is set up where it electrically isolates the power lines from the circuit that's actually connected to the person. So any kind of electronics that you actually add on, I've mentioned this before, but I'll mention again, it's really important that worst failure mode of this can never have the person connected to the power mains. That would be can be catastrophic. If you like put 110, 60 hertz across your arms, right across your heart, it actually can disrupt your heartbeat in a really bad way. So she is not risking her life by doing this here.
Yeah. So grade.
All right, so then let's make sure they see that little snappy electrodes.
Yeah.
Make sure it's really on there. be an extra in the matrix here.
Okay. So the white goes on your right arm. Left is black. Green on your right.
All right, so now you're gonna relax. And now, let's see, hit start. There's a beautiful EKG.
Very nice.
All right, and you can show,
So if you take a look at this thing right here, wow. Wait a second, annotate. Hold on, something just went wrong here. I need to get back into the correct sharing thing. Where'd it go? Hold on a sec. Damn it. Here it is. All right, so if you take a look, you can see she's got her.
all right, and you can show how you can like
Dag nabbit.
increase
Dag super nabbit.
or decrease the,
Oh, there we go. So you can see there's a P, the QRS, and the T wave. Okay, so let's just let her keep doing this a bit, and I will mention what's next.
show how you can like increase or decrease the, oh, too big, and so that little plus, whoop, come into focus there, little, there it is, plus minus there on the left side. And then you can also show, we can change, instead of 10 to 1, maybe go to 5 to 1 to kind of spread it out a little more. It's kind of pretty. So there we got a beautiful PQ.
So one of the things to really pay attention to here, what are we looking at? What is this actually a measure of? What is this a picture of? Somebody.
The electrical information.
Yeah, this is just the voltage measured on your skin. It's the voltage measured on your skin with those electrodes. And at this point, it's being generated primarily by the depolarization of the cardiac muscle, which is big enough that it shows up as a signal that you're measuring on these electrodes that are taped onto your wrists. So that's important right now to really think about what you're actually looking at. You're looking at the electrical voltage measured on your skin, but that's ultimately being generated by your heart. I want to. Can I can now. All right. So again,
QRST.
oh, we can't do. I was trying to do an annotate, but I can't. So there's the P, the QRS, the T. It's very pretty. The next part of the lab. What does it have her do for the next part of the lab? I don't know if you've got the lab manual in front of you. What does it say to do next?
Clench your fists.
Uh-huh. So let's see. Does anybody have any idea, any predictions? What might happen when she starts moving her arms around? What do you use to actually generate the movement in your arms and your hands?
Muscles.
Muscles, totally. How does the excitation and contraction of muscles happen? Y'all remember that whole excitation contraction coupling? What happens after a signal comes down the somatic motor neuron to excite a muscle cell? Somebody. This is just on your test. You better know this.
Acetylcholine is released and the sarcolemma is energized.
Yeah, and by energized, what do you mean by energized?
Or hits membrane potential.
And
The
so,
membrane potential goes up.
and then that creates a whole what? As the membrane potential at the neuromuscular junction goes up, what happens?
An action potential is created and calcium's released.
Exactly. So part of having a regular skeletal muscle contract is the sarcolemma is having these big waves of action potentials across them, right? So let's see what happens when Tina starts clenching her fist here.
We'll keep it at 5 to 1.
Yeah, I think 5 to 1 is good.
Yeah.
All right, so it looks like our subject is healthy. We see she's relaxed. We have a get it started. And now go. Move him around. Whoa. And then she's relaxed again. And it's back to normal.
All right, so what happened there? You could see, obviously it all got totally crazy, but why? What was happening? Why did it look all crazy?
Is that temporal summation?
No. I
Were
think
the
that-
electrodes picking up the electrical signals from the sarcolemma as well as the heart?
Exactly. Right. In fact, all of those muscles that moving your wrists and arms around are way freaking closer to the electrodes than your heart is. The heart is in here and is sending electrical signals all through the salt water of your body. But if you're doing this, these muscles are right here going. So that's what you saw there, we would call an electromyogram. The electrical signal measured on the skin that is coming from the depolarizations just of the skeletal muscle there. You know, so if you want to have a nice signal, you got to, that's why we make sure that the subject is relaxed, because skeletal muscle also depolarizes just like cardiac muscle when it's contracting. So if you contract skeletal muscle, it's going to show up as part of the signal as well. And in fact, as we could see, it totally overwhelms. You know, when all of that craziness was happening, the EKG was still happening. It just was totally hidden under all the noise. So does that make sense? So cool. So now the PR interval, remember that was, P was when that, in fact, let me go back just a second. Part of your write-up for this in the Moodle, not Moodle, it's not Moodle anymore, in the Canvas module, we have some PDFs of these different waveforms. Like one of the things you're going to do is just take this. Normally you would do it with your own, but you'll do it with Tina's. You print it out and you just label each of the different waves, and make sure when you label on the printout, you write down what is actually happening. Like this is going to be the P wave and it's atrial depolarization. This is the QRS and it's ventricular depolarization.
Okay, started.
And what should the delay be from the P to the QRS? From the atria depolarizing till when the ventricles start depolarizing.
0.1 or to 0.2.
Exactly, that intranodal pathway delay. So in the old days, you used to have to count little squares on the graph paper from the chart. But for this, we'll show you, there's just an easy way using a little marker, and we'll see what it is.
And now go.
Oh, so that, oh, she's got a great expression there.
Whoa.
Okay.
And then she's relaxed again. And it's back to normal.
Yeah.
All right.
Yeah, I mean, one of the few silver linings is actually kind of fun making these videos. And I've gotten way better at video editing.
Okay, and drop it right at the beginning of the P wave.
Here.
Oh, no, you can just like right there. You can just put it there.
Great.
So this is the kind of the automated, it can actually tell us, it just automatically tells you from where the marker is to where the cursor is, how much time it was.
At the
Beginning just at the rising of the QRS there. And now we can take a look up here. And we see the delta time is 0.12 seconds, which
Right. So like on your picture that you're going to print out that PDF, you're going to show the P, the QRS, the T, what they do. Make sure you also annotate it to show the PR interval, you know, because that's an important part of when you're looking at this EKG, kind of understanding what that time should be there and what's a good time, what's a bad time. This is a good time.
is totally normal. Woo.
Yahoo.
All right.
Okay.
All right, so that is, and you can see down here, EKG Pdf, I'm kind of highlighting it at the bottom. That's where you're going to find the PDF that you can print out her EKG, and where you're going to be able to kind of annotate right on it the P, the QRS, the T with little arrows, and again, say what they mean. So that is part one. The next part, in you know, that part you can do, you know, I'm going to just move on, given that we'll let you just do that on your own. After we're done with all this talking, you can review this if you want to review it, print this out, annotate it, and just make sure you understand what the different sections mean. Like on your lab exam, you know, that kind of stuff, that'd be the kind of question, like, you know, pointing to part of the EKG and asking, like, you know, what is this wave called and what's happening when we see this wave? So the next part, estimating the speed of the pulse wave. So, you know, here was your heart. Let's draw you. Here's you with your arm and your hand. And let's get a different color here. You know, when the heart, whoa, what's going on here? When the heart actually is squeezing, it creates a pressure wave, or it puts the pressure that goes out through your aorta. And that's kind of this pressure front that keeps traveling down the arteries. It goes through the subclavian, down the brachial, down the radial and ulnar, finally making it all the way to your finger. So there is a wave. Think about, you know, if you were in a swimming pool and you pushed and you'd make a little wave of water, and then that wave would keep traveling across the pool. That's kind of how the pulse happens. The ventricle squeeze, that's going to create this impulse that is then going to have to travel down your arteries to get to your like radial artery where you finally feel it. It's not like when your heart beats, all of a sudden you feel a pulse at your wrist. The heart will beat, and that starts this wave, pressure wave, that then travels down the arteries and finally shows up where you actually feel it. The speed that that pressure wave travels down your arteries is depending on a variety of things, including like the stiffness of the arteries and all that. So it's something people have been looking at, like trying to assess cardiovascular health just by looking at the speed of the pulse waves down arteries, because it actually is related to how stiff or how flexible the arterial walls are. Things that are stiffer tend to move through faster, more. So what we're going to do for this part is we are going to figure out the pulse speed. And maybe I'll go back to so if we're going to figure out the speed of the pulse wave. So back from like algebra, how do you figure out speed? Rate. What is the formula for rate?
Distance over time.
Exactly. It's just distance over time. So this is the classic thing, right? If you can drive 60 miles in 1 hour, it's like, oh my God, I'm going 60 miles an hour. You know, if you drove, 60 miles in a half an hour, then you're going 120 miles an hour. So it's just however far you went and divided by the time is going to give you the rate that you're going. So if we want to get the pulse wave rate, we have to get two things. We need to know the distance that it went and how long it took to go. Again, the distance, if we kind of draw this, there's a person here. We're going to use this little pulse transducer that goes on their finger. The pulse transducer basically detects movement. As if this is your thumb here, as the blood comes in and under pressure fills it up, the thumb will get a little bigger. And when the blood pressure goes down, it gets a little smaller. So the thumb is, the volume of the thumb is kind of going up and down. It's kind of swelling and contracting and swelling and contracting. And this pulse transducer, which you wrap around your finger, actually detects that movement and creates an electrical signal. It's a transducer. It transduces, it's a mechanotransducer. It transduces the movement of your finger as it kind of swells and relaxes during the pulse into an electrical signal that it sends to the computer. So this pulse transducer is just a mechanotransducer. So we can see the pulse at the finger because the finger is going to be moving, kind of swelling, relaxing, swelling, relaxing. The blood's going to go, here's what is going to generate the initial. So if I guess I go back, hold on, let me not get confusing here. For distance, if I want to measure the distance, it's going to be really simple. What do I do? How am I going to measure the distance that the pulse wave had to go?
Measure from your heart to the end of your
Yeah,
finger.
exactly. We're going to use a tape measure. like 10 centimeters below your jugular notch. The jugular notch is where your clavicles are resting on your sternum. About 10 centimeters below that, you assume that's about where the aorta is coming out of the heart. And then you would just do your best to put the tape measure on your skin and figure out, yeah, again, it's going to be approximate, but you'll get a pretty good measure of how far, what's the distance that the pulse wave had to go. So that part is pretty straightforward. And then how are we going to measure the time that it took? For the time, we need to know when it started and when it got there. So how can we know when it started? How do we know when the pulse wave started? What is creating the pressure that starts the whole pulse wave to begin with? What's actually generating the impulse of pressure that starts the pulse?
Systole?
Exactly, ventricular systole. So when the ventricles squeeze, when we have systole, that's going to generate a pressure wave that's going to start then traveling down the arteries. However, can I figure out when systole, ventricular systole is occurring, given our setup here? Oh, this, you should know this.
Looking at the QRS complex.
Exactly. Right, the QRS, ventricular depolarization. Ventricular depolarization, that is going to be when the ventricles are contracting and squeezing. So that means we actually have a measure of systole. All we got to do is see when the QRS complex is occurring on our subject. In terms of when the pulse gets to the finger, we're going to have this little pulse transducer, and we can actually see the pulse arrive at the finger. So this next part of the lab, we have two things we're measuring off of our subject. We're going to be measuring their EKG, because that's how we're going to know when systole occurs and when the pulse wave begins. We're going to have this pulse transducer on them so we can see when the pulse arrives at the finger, and that's going to be able to give us our time. If we look at how long did it take from the QRS of the EKG to start and the pulse arriving at the finger, that's going to give us our time. And then we'll know the time, we measure the distance, oops, and then we will, where did it go? There it is. Oh, it's gone. So once we know the, oh, there it is. Once we know the distance and we know the time, we can calculate the rate. So follow along now as we do part 2. Share screen. Hold on. Here we go. All right, so now it's time for the pulse transducer. So pulse transducer.
Wait till all this goes wireless.
And just put put that on there and have it nice and firm, but not cut off her circulation.
So I'm
And
gonna show a sample.
yeah, so now start it up again. And there, I'm gonna zoom in on the,
You want that any bigger?
so just pulse transducer on the top, EKG on the bottom. Even though they look kind of similar, they're actually very different things.
So why, so this is really important at this point, that you really understand how these are radically different things, even though they look pretty similar. You look at them and they look very similar. They're the same rate. You know, what is the EKG on the bottom measuring? What is the actual thing that is measured here? We mentioned it a few moments ago as well.
Electrical signals.
Exactly. It's measuring the electrical signal on your skin due to your depolarization of your cardiac muscle. This pulse transducer, which is also kind of going up and down at the same rate as this, what is it actually measuring?
When the pressure wave arrives at your finger.
It's actually measuring the movement of your finger.
Oh.
It's measuring them. It's your finger going zzz, zzz, zzz. So this is an actual just mechanical movement that is being detected by the transducer, and the computer's displaying it this way. So it's just a very different thing when you're looking, and we have printouts of this as well for you to work with in your lab write-up. Make sure you really think about how the EKG is electrical activity of your heart. This pulse transducer is just the movement of your finger as the pressure at your finger kind of goes up and down as your pulse. And, you know, in that same marker system that we use to measure the PR interval, we can now use to look at the difference in time from the QRS, when the pulse wave starts due to systole, to when it arrives at the finger, when we can actually see the finger starting to swell out. So let's continue here.
All right.
Take a good notch.
Or the dichrotic notch. All right, so now let's stop that. And now let us click and set a marker. Take the marker to the QRS. So ventricular contraction. Perfect. And now let's put the marker to when the pulse is arriving at her finger there. And oh. So there it is. Now I'm moving over to see the time. And it looks like 0.3 seconds. Pretty. So you're going to need to take note of this, because part of your write-up, when you're kind of calculating that rate, like we said, rate is going to be distance divided by time. So this time is going to be important for you to actually calculate your rate. Nice. Now we got to see how the distance that the pulse wave went. So 10 centimeters below her jugular notch is where her aorta leaves the heart. And then following the subclavian to the brachial, down to her finger. Right. So obviously your blood vessels aren't going through the air. Usually when we're doing this, we take care to really kind of push the tape measure against your skin and get a more accurate, like, again, we were under constraints of not modeling bad behavior by like touching each other during, you know, 6 feet apart. So, but normally you would be
you'd be taking a much more accurate measurement of this. But you know, I calculated what we're getting with this. You still get a perfectly fine value. So you can use the number that she comes up with. It works fine for getting a reasonable number.
Yep. So
And
maybe 5.
cool.
Right, so you're going to need to know that as well. So now we have all the information we're going to need to can actually calculate the pulse rate.
All right.
So that is that. I realize what I'll also do is upload some old data of other people's pulse rates, not pulse rates, pulse velocities. So you can compare, because part of the thing is how does yours compare to other people's? I realize I didn't upload that yet, so I'll find that and I'll upload that for you once we're done with all of this. I'm taking a note for myself right now. And I'll just put that in that same module there. So any questions about the pulse rate? Not pulse rate, I'm saying it again. The pulse velocity, pulse wave velocity.
So I was just curious, you mentioned in the lab notes, it's used for assessing arterial stiffness and cardiovascular risk. Would a lower pulse rate indicate arterial stiffness, or
No,
how would
so
it work?
I think actually higher velocities tend to be more stiffness. Like think about like a string, if it's more taut, it vibrates faster. So I think things that are more flexible tend to have a woo woo versus. So I believe more stiffness would be faster. And the stuff I've read about actually doing that, they typically don't just look one place. They actually look at the pulse wave velocity on a variety of different locations. And it's also still something that it's not like a normal clinical thing that, you know, they use, but it does seem to be correlated with that. And people have brought it up a number of times as a way to try to assess cardiovascular health. But it's not, as far as I know, it's not a typical way to try to decide whether somebody's okay or not.
Okay.
But it's still kind of cool. So the last part is going to be the just looking at the pulse, taking off the EKG stuff. And I think, trying to remember whether or not I actually.
All right, so now it's time for the pulse transducer.
No, wait, stop. Okay. Did I put it on? I think I put a picture in here.
All right, so now she's taking.
No, I didn't. Okay, so let me share one more thing. So if you look at your arm, so here's your heart, here's you, here's your arm, here's your hand. Blood comes out of your heart, goes down the brachial artery, which hopefully you all felt. It splits going off towards the thumb is the radial artery. But then there's also a branch going towards your pinky called the ulnar artery. And then there's this what's called the Palmar Arch. And so why this is interesting is there are more than one. If you're going down to get to the lower arm, the main pipe is the brachial artery. But once you get past the elbow, there's two ways to get to the hand. You can either go down the radial artery or you can go down the ulnar artery, and they interconnect. This we call it anastomosis. Whoops. Anastomosis. That just means that there are interconnections and there's more than one way to get to the same place. So if I'm trying to get to my finger here, I can either go down the radial artery and go from this side, or I can go down the ulnar artery and come around from the other side. And so for this last part of the lab, it's kind of demonstrating, it's this idea of pressure points. I was saying if somebody's bleeding, knowing where these arteries are and where you're feeling these pulses can be very useful. If somebody's having bad hemorrhaging in their hand, knowing that the brachial artery is the main hose supplying the lower arm, if you put pressure, right there, you basically are stopping blood flow to the entire arm, or entire lower arm. Whereas if you just stopped like this artery or this artery, the blood can always come around from the other way because of this anastomosis here. So we will see this demonstrated with Tina and pushing on the different arteries. Oh, where did it go? There it is. What? Hold on one second. Something just went wrong with my sharing. Let me share it again. Oh, here we go. All right, so here we go. So now we don't care about EKG. We're just looking at the pulse.
Just has the pulse transducer.
Okay, so then I'm gonna start this.
Start this.
I'm gonna pull this down, make it a little bit bigger.
Okay.
Start.
All right, you can actually increase the magnification a little bit on there. Okay, so we have a nice pulse.
Okay, so
And-
now it's my brachial. Yeah, okay.
So there you go.
Nice. Firm pressure.
All right,
So you saw that. That's actually a useful thing. Like if somebody's got a really bad, they're bleeding really bad down somewhere, they just sliced their fingertips off in a horrible bandsaw accident. You just push right there and you're pretty much stopping the majority of the blood flow to the lower arm there. So it's a very useful thing to, even though this is kind of like, just a lab, it's a useful piece of information.
now take that off.
Okay. You wanna film?
All right, and it's coming back.
And then show her without it, her hand there anymore. Okay.
All right, now go on to your radial. It's down,
Nice.
but it's still there.
Whoa.
Whoa. Whoa. All right.
So
Go on to your ulnar.
So again, here you can see it's going down. Which artery, do you think the radial or the ulnar is supplying the majority of the blood to her finger?
The radial.
Yeah, totally. You just saw that when she blocked the radial, there was very little. There was a little bit coming through, but not that little. I mean, but not that much. Whereas when she compressed the ulnar artery, there's still quite a bit of blood making it through the radial. So for her, it's obvious that the ulnar and the radial are not equal in supplying the two sides of the of that loop.
So you have the majority of it come through your radial.
Interesting. Yeah, that was interesting.
All right, so now you're gonna put it on both. Whoop. Ready?
Right.
There we go. Nice.
Right, so that makes sense. If you get both of them, then again, it's the same as if you were compressing the brachial artery. You know, you're just totally stopping all blood flow down into that palmar arch.
All right, and then beautiful.
So that is basically it. And the PDFs down here, let me get my little annotator. You know, again, this one is part one. This is just the EKG printout that you're going to want to kind of annotate with the P, QRS, and the T, and with the PR interval. Just make sure you just get to know the basic EKG and the different parts and pieces and what they mean. The EKG and pulse, that one is going to show both of the EKG and the pulse at the same time. And on that one, you should also annotate that to kind of show how you are detecting the timing of the pulse wave. So again, it's just basically, again, you should, if you don't remember what started, how do we know when the pulse wave begins?
QRS complex.
Exactly, that QRS complex. And then we can see the amount of time from when that happens to when you actually see the pulse showing up at the see. So in fact, I can just open this up and you can see it. Right, so you'll get this printout and then you can annotate and kind of show how you can use this, the EKG on the bottom, the pulse transducer on the top, and how you can use this information to figure out the time it took for the pulse wave to reach the finger. And then again, we have the distance that it had to travel from watching Tina use the tape measure on her arm. So that's, you'll want to do that. And then
So on the QRS, where do you put the marker?
we just kind of put it right at the top of the QRS.
Okay, and you measure to the top of the transducer line.
That's basically that's what we were doing there. So it's like, yeah. Do I have, I can annotate again. It was basically, QRS is where the ventricles are contracting, and here's where we see the pulse is showing up at the finger. So we kind of measured from, there to there and looked at that distance.
Okay.
And then these other ones are just showing kind of what happens when she's blocking different parts, right? Well, ignore that. But you can see the normal pulse and then it's attenuated. So on these, you probably also want to kind of annotate them and show normal pulse and then show that pulse is smaller, but it's still there. And in your discussion, talk about both why is the pulse smaller, but also why does the pulse not disappear? Because part of the main part of part 3 is understanding there are certain things you can push on that are going to make the pulse go away, certain things that are not going to make it go away, but will affect it, and kind of understanding how that works. So these PDFs are doing that. And so are there any questions about any of these? It's not, I feel for you guys in that it's not as fun watching somebody else stick electrodes on themselves and watch a video of them. But, this is still gonna give you the basics of what it looks like and, what the EKG is all about and what the different parts mean. So in your discussions, make sure, it's clear that you kind of are talking about, kind of what the waves are, what the different take-home messages are from these different parts of the lab. I will also, I haven't added in here, I will add in a part to ultimately submit your write-up. I'll make it due in a couple of weeks. But what I need to do first is grade the ones you've already put in, as well as grade your exam, which I have not had a chance to even open up yet. So my plan is to get the lecture exams graded so you can get feedback on those, as well as start giving you feedback on the labs. So you should start writing this one up, but it's not going to be due for a couple of weeks. And like I said, the quiz will happen on Monday, and it will be a kind of online click through kind of thing. And are there any comments, questions, or otherwise as we go into another weekend of living in a box?